Hello, everyone. This is the lecture for section 4.6 and 4.7 for our Math 210S portion of the course, solving exponential and logarithmic equations. Okay, so at this point, right, we know what an exponential graph is. We know what a logarithmic function is, right? In numerically, right, we know how to interchange the two, but what happens when we actually have equations and functions that we need to solve, right? That's what this section deals with. We're going to start solving logarithmic and exponential equations, okay? And the way that we're going to do that is I'm going to give you guys a couple of we're going to sort of take all the application out of some of the equations, just learn how to solve them, right? And then we'll stick in some real world applications to them so that we get a nice exposure to how to actually solve these, okay? All right, so the first thing I want to do, right, is I kind of want to revisit this thing, okay? And I'm going to highlight it in pink. In a previous example, I think I put little fireworks around it and stars and smiley faces, right? This is our magic boomstick right here. This is the thing that gets us to change between the two forms. So if I have a logarithmic version, I can change it into the exponential, okay? And if I have the exponential version, I can change it into the logarithmic, okay? That's simple. This is all of it, the thing that's highlighted in pink, okay? Now, how does this actually work? Okay, I'm going to do a couple of examples. Okay, I'm going to leave that there. There we go. Okay, I'm going to do the one on the right first. Okay, but the idea for how to solve these out, right, is we want to get the exponent bit by itself. So if you guys take a look, right, uh, whoops, not that side. It looks like I'm going to have this thing. I'm going to have the exponential form sort of on for both of these, right? The way to solve it is we want to get it into this form. We want to turn it into the logarithm. And when we do so, right, then we get something that we can plug into a calculator. Okay? So that's sort of like the point for this whole section. So let me try. I'm gonna show you guys how to do this first one, the one on the right, right? Okay. So the idea is I want this thing by itself. Okay. You are correct in thinking that there's a multiplication in between here. So I'm going to go ahead and do divide by 625, divide by 625. Okay. And what you get, when you do this, right? Let me make sure before I lie to you. Divided by 625. I think yep, that's what I thought. When you do this, you're going to get 5 to the 3x plus 3 is equal to 1 over 5. If you reduce it down. Okay, so now we have that exponential version, right? We're going to try to change it into the logarithm. We can see what base it is, right? You guys see it's a base 5, right? So I have this side. I'm going to turn it into the other side, right? So then if I do that, this is telling me, right, uh, log base 5 of 1/5 is equal to 3x plus 3. Okay? Now, this thing, I'm going to be using a little bit of the exponent rules. Okay? That is the same thing as log base 5 of 5 to the negative 1 power. And that's going to be equal to 3x plus 3. Okay? I want x by itself at this point, right? So I can go ahead and do minus 3, right? So then I have log base 5 of 5 to the minus 1, 1. Minus 3 is equal to 3x, and I'm going to grab this, take it up here, and then I can divide by 3, right? So log base 5 of 5 to the negative 1 minus 3 divided by 3 is equal to x. Okay? This thing, That is -1. So this turns into -1 minus 3 all over 3 equal x minus 4 over 3 is equal to x. We are done. That's it. Okay. 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 Let me do the next one. So in this situation, in the one that's on the right-hand side, right, the numbers sort of cleaned up nice, right? What happens if they don't, right? That's what's going to happen um, on the left-hand side, okay? The process is still the same. I'm going to grab that thing and try to get it by itself, right? So there's a multiplied by 20, so I want to divide by 20. Okay, that's going to be 5 is equal to e to the 2t. Okay, now we have the exponential version. We need to change it into the logarithmic, right? Okay, log base e of 5 is equal to 2t. Okay, that is just me using this thing. That is just me using that thing. Okay, and then from here, I need t by itself, so I can divide by 2. Divide by 2. And if you remember from the previous section, right, a log base e, that is equivalent to just ln. So I can do ln of 5 divided by 2. We are done. I can grab this and throw it into a calculator and get a numerical or a decimal value if I wanted one. That is a horrible box. Whoosh. There we go. Got it? Okay. Okay. From here, I'm going to make you guys try a couple. Okay. There's a couple quick checks here that I want you guys to try out, and I don't know why you did that. It moved some of the pages around. Oh, man. Okay. Give me a second. Darn pages moved around for some reason. Oh, come on. There we go. Okay. I'm going to try to move all the pages right now. There we go. All right. Okay. Like I said, quick checks. Okay. We'll do this in class. Let's go the other direction. So in the previous examples, we had the exponential version, and we needed to change it into the logarithmic version to solve it out. Okay. In these examples, we have the reverse. We have the logarithmic version. We need to change it into the exponential version to solve it out. Okay. These two are going to require a little bit of our logarithm rules in order to get them right. Okay. No matter what, let me start with the left-hand side first. You guys see how it's log, right? All the logs are the same. Yeah? Okay. So I'm going to go ahead and combine these two. So if you guys remember, if you have two logarithms that are separated by a negative, right, I can do this. Log 3x minus 2, whoops. This is equivalent to 3x minus 2 over 2, right, has got to be equal to log of x plus 4. Okay? If the two logarithms are the same, and both of these got to be equal to each other, notice what it's doing there, right? Both of these have to be equal to each other. Then both of these things, the things inside the parentheses, have got to be equal to each other, right? So 3x minus 2 over 2 has to be equal to x plus 4. We now get to turn this into just a good old algebra 1 problem, right? So 3x minus 2 is equal to 2x plus 8. Solve stuff out, so minus 2x plus 2 plus 2. x is equal to 10. Bam. Okay. So that happens because this happened right here, that we were able to use our logarithm rules to sort of simplify stuff down to something simple, right? And then solve it out sort of using kindergarten math, right? This stuff, okay? Sometimes that does not happen. So here, everything's done. We can't do anything else to combine anything, right? So what we have to do here is we got to change this into the equivalent exponential versions to solve it, okay? So let me write this down over here again, right? So if you have a to the b is equal to c, that is equivalent log base a of c is equal to b. Okay, remember, right? This is our magical rule right here. This is the magical statement. Okay, okay. 2 to this power has to be equal to that. So then this is telling me x squared minus x minus 2 has to be equal to 2 squared. Okay. Minus x minus 2 has to be equal to 4. So at minus 4 minus 4, x squared minus x minus 6 has to be equal to 0. Hopefully you guys remember this thing, right? So I'm going to do it really quick, right? I need two numbers. I'm going to do it over here. I know I haven't done it explicitly for a very long time, but we'll do it again, right? Minus 6 minus 1. Multiply and add. So I need two numbers that multiply to minus 6 and add to negative 1. If you guys thought negative 3 and 2, you are right. So that means this thing down here simplifies to x minus 3, x plus 2, and this has got to equal to 0. So then each one of these x is equal to positive 3, x is equal to negative 2. Okay? Now, logarithm version is a little funky because remember, we added a new rule that we can't do. Right? We cannot take the logarithm of a negative number. Okay? So what we got to do is we got to make sure that both of these answers are able to be plugged into here. Okay? So in particular, we are going to double check. There we go. We're going to double check that this is not negative, that x squared minus x minus 2 is not negative when we plug in both of these values. Okay? And for that, we just plug it in. So I'm going to go ahead and do this, right? So x equal 3. If we plug in x equal 3 to that thing, right, it's going to be 3 squared minus 3 minus 2. That's going to be what? 9 minus 3 minus 2. So that's going to be 4. This is good. This checks out. Bam. Okay. This one. When x is equal to negative 2. Let's double check and make sure that that one works, right? Minus 2 squared minus a minus 2 plus 2. Oh, so, sorry, minus 2, right? This is going to be 4 plus 2 minus 2. This is also 4. This is also okay. Okay? That means both of these answers are valid. Okay? In the event that one of these, either this one or this one, turned out to be negative, then you would have to cancel that answer out. So basically this one wouldn't work, right? Or this one wouldn't work. One of the two. Okay? That's why we have to check. And particularly, we are checking, right, to make sure that we are not plugging in a negative number into the logarithm. That's it. Okay? All right. To practice a little bit, I'm giving you guys some practice. Yeah? Okay, okay. Now let's get into exponential and logarithmic models. Okay, so you hopefully remember, right? When we first started doing exponential functions, there was a handful of functions that I gave you. Okay, in particular, the first one, compound interest formula, right? This one was the one that was a p times 1 plus r over n to the nt. Okay, and then the next one down, this one was the continuous. Okay, this one had the ae to the rt. Got it? Okay. Each one of these had their portions, right? They had the definitions for each one of the variables. Okay, so if you need to review those, go back and watch that video. I'm just putting them in there because I will review them during class. Okay, but more importantly, what I want to do is get down to the examples. Okay, so I'm going to be doing an example. The first one is going to be investments. So this is going to be using the financial version. Okay. And then the one below is going to be doing the continuous equation. Okay? Okay, so let's go ahead and do this first example. Let's do part A. So suppose we had, right, $3,000 in an investment account paying 3% compounded quarterly. Okay, first of all, I want to find an equation. So I need to find this thing. I need to find the A of t being equal to, right, P 1 plus r over n to the nt. N. This is quarterly, so n is equal to 4, right? R is equal to the 3%. 0.03, remember, we can't plug in the decimal value itself. We have to convert it to, sorry, we can't plug in the percentage. We have to change it into the decimal, okay? And then what's missing? P, my principal. And that was my $3,000, right? So my equation is A of t is equal to 3,000, 1 plus 0.03 divided by 4, move that to the 4t. This is my equation, right? You guys remember that from exponents? This is the same problem, by the way. Forgot to tell you guys that. Yeah? All right. I'm going to clean this up a little bit, right? A of t is equal to 3,000. And let me do that 1 plus 0.03. 1 plus 0.03 divided by 4. 1.0075 to the 4t. Okay? Either one of these is perfectly fine as an answer. Okay? That's it. This was A. We did A. B. B is asking us, find when the value of the account will triple and use a graphing utility to verify an answer. Okay, so I'm going to leave the verify the answer for you guys to do on your own, but this is essentially what we did in our first example back in section 4.1, 4.2. Okay, but now we're actually going to solve this. This is the new bit. I am actually going to solve out exactly when that value is going to triple. Okay, so if initial, right, was the 3,000, right, then triple is equal to 9,000, right? So I want to find when this equation, right? I want to find when this equation becomes triple the original amount, right? So it's exactly how you think it's going to be. I'm going to do 9,000 is equal to 3,000, 1.0075 to the 4t. Okay? Okay, here we go. I need this thing right here. I need it all by itself, right? So there's a multiplication between the 3,000 and everything else. So divided by 3,000 divided by 3,000. Okay. 3 is equal to 1.0075 to the 4t. You guys see how we have now the exponential version, right, of what we need to solve. We need to change this into the logarithmic version. Okay, so I'm going to write it over here. A to the b is equal to c is equivalent to log base a of c is equal to b. Okay, I'm going to highlight it in pink so we don't forget it. And we can make it stand out since I've been highlighting it in pink for the last couple sections here. Okay, so then this means log of 1.0075 of 3 is equal to 4t. Okay, I need t by itself, so I can divide by 4. Divide by 4. T is equal to the logarithm of 1.0075 of 3 divided by 4. Okay, now we at least have an answer, right? I am going to put that into Desmos. I'm going to show you guys how to do it really quick. Okay, you guys see how down here there's that keyboard that can pop up, right? We have functions. Scroll all the way down until you get to log. You see this one that says log base A? It gives you the little... So it's allowing you to put in a subscript there, right? So 1.0075 is my base. What's in here is a 3, right? Close it all up and then divide by 4. Okay? And we get 36.7575. How's that look? Yeah? Oh, there we go. Okay. So now, remember what we were doing, right? We were trying to find when the account will triple, right? Okay. The t that we're plugging in, right? T is equal to years, right? And A of t, what, right, was equal to investment amount, right? Okay. That if we gave this function, if we gave this function right here a year, it'll tell us how much money we had. And I don't know why that 3 disappeared, but there we go. So if we gave that function a year, it'll give us how much money we have in the account, right? That's what we just found. That's this. Okay? We just found that's a big, huge space. $36.75 years. I believe if you go back to the notes for section 4.1, 4.2, we used an estimate. We got an estimate. It was 35 point something, right? Or sorry, 36 point something, right? This ends up being the exact value. This is the exact value. So in the previous sections, we were getting estimates, right? These are exact values now. We're able to solve them out accurately, not using a graphing calculator. Okay, but no matter what, double check these with a graphing calculator. Okay, I always want you to double check your work. Okay, all right, let's move on to the next one. So this one dealt with radioactive samples. Okay, so first of all, A, just as usual, give me an equation, right? And B, it's asking you when will the radioactive sample decay to half its original amount, right? Okay. So for A of T, this was this thing, right? So A e to the RT, we needed the little a, that was going to be our 150 grams, right? And our R was decay, negative 1.5%, right? We can't plug in the percent. We have to change it into decimals, so negative 0.015, right? Negative 0.015. So then my A of T, 150 E to the negative 0.015 T. We are done. That was it. That was it for part A. We did part A. Okay. Part B is asking us find when it will decay to half its original amount, right? So initial, right? Just so we can get our thoughts right. Initial was supposed to be, well, it is for this problem, right? 150 grams. So then therefore, right, half should be 75 grams. Okay, and just like before, we need this equation, right? We need this one to be equal to that half. So we solve it out. 75 grams, right, is equal to the 150 e to the negative 0.015 t. And we're trying to solve for the t, okay? In terms of our exponents, we need to get this thing by itself. Okay, so that's exactly what we're going to do. There is a 150 that's being multiplied, so divide by 150. Divide by 150. Okay, this leaves us with 1/2 is equal to e to the negative 0.015 t. Got it? Okay, we now have the exponential version, right? We can now change this into the logarithmic version. Okay? If we do that right, so I'm going to go ahead and write it again over here, right? A to the B is equal to C is equivalent to log base A of C is equal to B. I'm going to highlight it in pink like I've been doing for the last couple sections, right? Okay. Log base E. Let me actually give myself a little more space. Log base E of 1/2 is equal to negative 0.015 t. Okay, I need to solve for t so I can divide away that negative 0.015, right? So divide by negative 0.015, divide by negative 0.015. T is equal to, remember, log base e is equivalent to ln of 1/2. Actually, let me just go ahead and do this. I'm going to go over this way. Okay. The log base e is ln, so this is saying that t is equal to ln of 1/2 divided by negative 0.015. Okay, and if we plug that into Desmos, I'm going to bring up Desmos really quick, wherever I can. There it is. Okay. Now, we know what the answer is, right? it turns out we don't have to go through the functions button on Desmos. We can just type in ln on your phone, okay, of 1/2, 1 divided by 2, okay, divided by negative 0.015. And what was it that we got again? Look at me go way too fast. 46.21. 46.21. Okay. I'm going to highlight all of that in green and then square it out in green. Horrible square. There we go. Okay, so final answer, right? The radio sample will decay (46.21 days. Okay, so that means this is what we just solved out, right? If we start off with 150 grams of this radioactive sample, and it decays at a continuous rate of change of 1.5% each day, then in about a little more than 46 days, it'll reduce down to half. You'll have 75 grams of your radioactive sample left. Cool? Simple enough? All right, cool. Okay. I've got the same examples now this time around, right? I'm going to make you guys find the actual times when these things happen. Got it? Okay. Okay. Same thing. Same thing. I'll give you guys a lot of time for these. Okay. One more model I need to show you all. Okay. It's Newton's law of heating and cooling. This one has a pretty interesting history behind it. Okay. It's both for heating and cooling. It describes heating and cooling of an object. Okay. This is the equation for it. And I think when I copy pasted it from the book, it just looks nasty, but it's supposed to be T, big T of little t is equal to a big A, e to the k t plus some t sub s, okay? The temperature of an object, right, that is in a surrounding air temperature, so sort of like an ambient temperature, okay? And suppose that ambient temperature is T sub S, right? Okay, will be this. This is going to be the equation that describes it, okay? Little t is the time, okay? A is the difference between the initial temperature of the object and the temperature of the surrounding, okay? And then K is a constant, and we call that the continuous rate of cooling or of heating of the object, okay? That's going to be different for every scenario, okay? So depending on whether something is heating up or cooling down, that K is going to be different, okay? The thing that people tend to mess up on is that A, okay? It's the difference between the initial temperature, okay, and the surrounding temperature. If something is heating up, right, then the initial temperature is going to be lower than the final, right, than the surrounding, okay? And in reverse, right, if something is cooling down, right, the initial temperature is going to be really hot and the surrounding temperature is going to be very low. So that's going to be a positive one, okay? Okay. So without further ado, I want to run through an example, okay? This kind of problem is going to require a fair amount of everything that we just learned, okay? So take your time with it, okay? Rewatch this example in particular lots of times, okay? So suppose I had a cheesecake that I took out of the oven, right? And that cheesecake, when I took it out of the oven, was 165 degrees Fahrenheit, okay? And I placed it into a refrigerator that's 35 degrees Fahrenheit, okay? After 10 minutes, the cheesecake is cooled to 150 degrees Fahrenheit, okay? How long will it take that cake to cool down to 70 degrees? Okay, and I want to use the graphing utility to verify my answer. Don't get scared, okay? We know that the formula is going to look like this. It's going to be a big T of T, right, is equal to some big A, oh, E to the K T plus TS. Okay, we're going to try to fill in as much as possible for this thing. Okay, and the two things that we can fill in automatically are these two things, the TS and the A. Let's start with the A. Okay, the A is the difference between the initial temperature, right, and the ambient temperature, the surrounding temperature. Okay, this cheesecake started out at 165 and is being placed into 35. So that is going to be 165 minus 35. 130. Okay. Notice the order I'm putting it in, right? The initial temperature minus the temperature of the surroundings. I'm taking this cheesecake, which is already at 165 degrees, okay? And I'm putting it into a fridge at 35 degrees. Okay, so it's going to be the initial minus the ambient. Okay, we have A, T sub S. The surrounding temperature is going to be the temperature of the fridge. Okay, since we're grabbing the cheesecake and we're putting it in the fridge and leaving it there, okay, since we're grabbing the fridge, or grabbing the cheesecake, putting it in the fridge and leaving it there, that's it, right? That's just it, right? That's the ambient temperature that the cheesecake is going to live in at this point. Got it? So we can fill in a fair amount of stuff already, right? So that means big T of little t is going to be 130 e to the k t plus 35. Okay? We still don't have a model yet because this is missing. We don't know what k is. Okay? We were able to do all of this work up to here due to this right here, the very first sentence of our problem. Okay, to find k, I'm going to use this bit, that after 10 minutes, a cheesecake is going to cool down to 150 degrees. Okay, so this means that my point, right, for this thing is going to be 10, 150. This is basically my little t, and this is going to be my big T, right? At 10 minutes, my cheesecake is 150 degrees. So long as I plug this in, right, and run with it, I should get my K, right? So that's exactly what I'm going to do. I'm going to grab this. I'm going to go up here. So 150 has to be equal to the 130 EKT, okay, plus 35. At this point, right, I need my K. Whoops, and I forgot the T. Oh, come on. I've got this tablet thingy in front of me. K times 10 plus 35. Sometimes it's annoying. It doesn't erase correctly. Okay. So you guys notice now, right, with the thing that I just wrote down, the only thing that's not solved is the K. So I can presumably solve for my K. Okay. I need this thing by itself. The e to the K times 10. I need that thing by itself so I can hit it with my exponential to logarithmic conversion thing, right? And then solve it out for K. So I'm going to do the moves, right? Minus 35, minus 35. This is going to be 115 is equal to 130 e to the 10k. There's a multiplication in between, so divided by 130. Divided by 130. 115 divided by 130 is equal to e to the 10k. And let me go ahead and cancel stuff away while I'm at it. There we go. We have our logarithm, or sorry, we have our exponential version, right? I get to change it into my logarithmic version. Okay, I'm going to write it. Let's do it over here. Not that color though. A to the B is equal to C is equivalent to log base A of C is equal to B. Okay, I have the from this equation, right? From this conversion thing that we've been playing around with, we have the left side, right? We have the left side. We get to change it into the right side. Log base E of 115 over 130 is equal to 10k. Divide by 10, divide all this by 10, right? I'm going to go ahead and go up here. K is equal to, log base E is ln, right? ln 115 over 130 divided by 10. I'm going to go into Desmos again. One more click over. There we go. ln. Use your parentheses correctly. 115, whoops, 115 divided by 130. All of that divided by 10. Negative 0.0123. Okay, we're getting there. We're getting there. I'm actually going to hide both of these put together. There we go. There we are. Okay. We found our K. It makes sense, right? So if you take a look at our scenario here, right? We took a cheesecake out of the oven and put it into a refrigerator. So that means my temperature should be dropping, right? Mathematically, that means my K should be negative. We're good. Okay. So then, model. Our model equation for this scenario, right, is going to be T of T is equal to 130 E to that thing, negative 0.013, right? 123 T plus 35. I'm gonna grab this. I'm gonna bring it down a little bit just to separate it. Oh, look at that. No, don't do that. No, don't do that. There we go. This is supposed to be a 5. Okay. And that's supposed to be an F. Bam. Okay. Now, the original question, we're not done yet. I know. I can hear you all grunting from here. Okay. My original question was this. How long will it take the cake to cool down to 70 degrees? Okay. It's exactly how you think. We want that big T. We need this thing, right, to be equal to 70 degrees. So we set that equal to 70 degrees and solve out. So here we go. 70 is equal to 130 e to the negative 0.0123 plus 35. 0.123 t. I forgot the t. That's my bad. Plus 35. Okay. It looks like I need that t. Okay. Which means I need to solve this out for this. I need to get this by itself so I can do the logarithm thing again. Minus 35. 35. So this is going to be 35 is equal to 130 e to the negative 0.0123 t. Divide by 30. 130, sorry. I'm going to go up here. 35 over 130 is equal to e to the negative 0.0123 t. We have it in the exponential form. I need the logarithmic form. So I get to hit it with this thing again, with our magical expression there to turn stuff from logarithmic to exponential and vice versa, right? So log base e of 35 over 130 is equal to negative 0.0123 t. I want t by itself, so I get to divide by all of this. Negative 0.0123 divided by negative 0.0123. T is equal to ln. And I need to give myself some room, don't I? Or maybe I should just not write that big, huh? How about that, huh? T ln 35 divided by 130 divided by negative 0.0123. And if I throw that into a calculator, ln 35, whoops, divided by 130 divided by negative 0.0123. $106.7 about. This question always comes up. How many decimal points? 1, 2 is healthy, so I could have put down 106.68. That's fine too. Okay. Now we're almost done. I swear. I swear to you. The question was asking, right? The question was asking how long will it take the cake to cool down to 70 degrees Fahrenheit, right? If you remember from here, right, we were defining variables, right? We said that little t was time, right? And it was in minutes. And big T was temp, right? And it was in degrees Fahrenheit. Yeah? Okay, when we solved all this out, we got this. Okay? And that's a little t, right? So the cake will cool to 70 degrees Fahrenheit. That's what we were solving for, right? The cake will cool to 70 degrees Fahrenheit in 106.68 minutes. And I'm going to highlight that. Okay. So given this stuff, let me actually zoom out one click so that I can have the problem. There we go. This is a lot of stuff. I know. I know. Follow it along. Okay. Reread, rewatch the example over and over and over again until it makes a little bit more sense. It'll click a little more every time. Okay. So all we did here, right, was given all of these stipulations for this scenario right here, right, given all of this up here, right, okay, we found a final model. We found a model. That was this thing, right? You guys remember that? Okay. And using that model, we were able to find out a time, right, for when the cake was going to cool down to 70 degrees. Okay. And it's going to happen in about, what, a little more than an hour and a half? 106 minutes? Yeah. And there we go. Now, mathematically, I want everybody to notice this. This was, as I keep saying, right, this was our boomstick. This right here, this conversion from logarithmic to exponentials and from exponentials to logarithmic. This was the thing that made it happen. Okay? Okay. What comes up next? Let me get rid of that highlight. There we go. What comes up next? Some quick checks. Okay. One of them is cooling. One of them is heating. Okay. I'm going to give you guys a good, handful of minutes to do these. Okay. Just to get them right. Okay. And after that, we've got lecture questions. Okay. If there are any questions on the stuff that I just covered, ask me during our quick check time, during my office hours downstairs, or if you can find me in the tutoring center, I'll be there too. Okay. All right. That's that. Happy studying.